And thank you everybody for attending the session. I will be talking a little bit about the seismic design of accelerated bridge construction, especially the connections, and how that can help improving infrastructure resilience in central and eastern US. So a little bit of the outline, I will go and talk a little bit about some bridges that have been, where you can find the use of ABC in central and eastern US. Then I will talk a little bit of ABC connections, some of their benefits. I will show some alternatives of ABC, the challenges of ABC in central and eastern US, then some conclusions about that. So here you can see 3 projects where ABC was successfully applied. You can see on your left how the connection is between the substructure, the columns, and then you just come with the cabin and place everything on the field. So you will bring all the precast elements to the field. In the central picture, you can see how those walls are going to be connected. You have the footing there, and then you just bring the precast element and connect everything. On your left, on your right, you can see in between there are some holes. Those are it's a specific type of ABC connection also. So you will come and just put the columns on that portion of the structure. Here, another bridges, that the one on your left, it's in New York, and this one is the I-95, this part is in Virginia. Also, on those projects, ABC connections were used. And the connections, well, we'll talk about that. The connections, in this case, well, you will use precast elements. You can prefabricate those in your shop. Just bring them. It's a modular construction. You can have connections just not between the superstructure and the substructure. With this one, you can reduce some construction time, minimizing traffic disruption. I will talk more about the benefits later. In this image, you can see different type of ABC connections. Like you have the columns. You can connect the columns to the footings, but you can also have connections between footings. In case you have the capability of bringing the footing precasted and bring it in place and connect them, some portions of them. You can also connect the cab beam with the columns. But then you can have connections not only in the substructure, but you can have ABC connections between the slab, part of the superstructure, the girders. So you have different options if you want to go in ABC connections. So these connections are also precise because you have the ability to work this in your shop. Those are durable. You have quality control a little bit better than on the field. Also, you can provide the continuity of the strength across the joints. We need to notice that this strength needs to be provided even if you are in low seismic regions. It's not like just because you are in a low seismic region, you just provide the minimum. You need to be sure that those connections can sustain earthquake, seismic actions. So here we see the prefabricated column, I mentioned the cabin, and the different connections. So these connections have been a focus of research through all the country and around the world in the recent years, especially the structural components, and in this case the connections between columns, cabins, foundations, as I was talking, in moderate and seismic zones. So, mentioning some of the benefits of the ABC connections, as I mentioned some before, but here I'm just trying to put them so you can see them together. You can reduce the time for construction. You can be building at the same time different parts, like casting your columns your cabins, and then you just bring everything on field. So you're also able to reduce the traffic impact with that. You can improve safety. You can reduce hazardous work process. For example, if you have some connections between steel structure, you can reduce welding on field, and you bring them together. You can eliminate risk of some accidents. When you're working with that, you need just the crane, and then you're going to place your precast element. The cost effective. You will need less specialized construction equipment there because you're building everything on your shop. Less on-site fabrication. You will minimize also the impact of surrounding environment. And as I mentioned also before, some material quality and product durability when you're able to bring everything precast from your shop in a controlled environment. And here are just some pictures of the use of ABC connections. For example, in that case, you can drive your piles, and then you leave the portion of the connection, and then you bring your cabin, then you can continue with that. You can fabricate all your elements, in this case the girders, in your shop. And you can reduce traffic impacts. You don't need to close for a long period of time your roads. Those are some of the benefits. Then I will be showing some alternatives. These are not the only ones. There are more alternatives. I will focus right now only between the column and the footing or cabin, because those can be used for both. So we have grouted connections. We can have bar coupler connections, but I will focus my attention on pocket socket connections. This is a type of connection that I'm studying for my PhD in North Carolina State University. So I will explain a little bit more about the socket connection. So a socket connection is a connection where you have your precast column and you have a void inside your footing or cabin. You will just go insert the column on that void and you will fill with grout. So you have some tolerance where you can go and place your column. And those can be internal or external. Right now, in the literature, you will see a lot of research on internal socket connections. I'm developing an external socket connection. And the reason is like, imagine you have your footing or cabin and you need to place your column inside. You will need to make your footing or bigger or your cabin bigger. In this case, I'm just leaving outside the footing. Outside of the cabin or footing, I'm placing the column. So you will not have that void inside your structural element. And also, the connection between the column and the cabin or footing is not made through the reinforcement of the column. As Ty mentioned, if you increase the reinforcement of your column, that will add some demands to the footing. In this case, you will not add those demands. Those are not connected between them. So that's one of the reasons why we're trying to develop these external socket connections. And I'll show in some of my specimens. So you can see the column on the left and the external socket connection there, already casted with the footing. And here you can see a brief schematic drawing, the column going inside the socket connection, and some of the details of the socket connection. So the way that the external socket connection is connected to the footing is through reinforcement. That's the only reinforcement that is coming inside the footing or cabin. And here you can see a little video of how I connect those. So I have the crane hanging the column right now, and that's me moving everything. So you can actually do it fast. You can just check levels, see that everything is there, and then you put the ground. That's making everything fast, as we want in ABC. And I'm going to show a little bit of the response of those. So I'm not showing all the results, but in this case, the force displacement. So you can see how this system behave. The column, this is the response of the column, of all the system. And I put ductility, as Ty was mentioning in performance performance-based design and displacement-based design, we care about the ductility, how much we can reach fast yielding, and how will be the behavior of the column. So we can notice that we were able to reach ductility 4, which is roughly 6 inches of displacement. That's more than 8% drift. That it's enough. It's a lot of drift. And with that displacement, we were able to rupture the bars. That means we were able to allocate the plastic hinge outside the external socket connection. As Ty mentioned, we will know where the plastic hinge will be. So we know that it will be outside the connection, and we leave a capacity protective element, which is the cap beam or the footing, which, as also Ty mentioned, that's one of the goals that we want in design. I'm showing here some pictures of the damage at ductility 3. So that was a 5-inch displacement. We can see that all the damage is concentrated on the column. And we have some crushing of the concrete at that point. The bars were exposed before, so we can capture all and measure all the strains on the steel. That's why you don't see cover right now. Here, a picture of the bar buckling that we obtained when we displace 6 inches at the top. And the bar fractures. In this case, the first bar fractured, and then the other bar fractured. So we had 3 bar fractures. In this picture, I just want to show the location of the plastic hinge, that it was just above the external connection, where we had bar buckling and concrete crushing. But after cleaning the specimen, you can see that the footing we didn't have any crack on the footing. And the external socket wall had some radial cracks, but those appear at the beginning of the test, just due to the expansion at the beginning of that confined concrete wall. But then we didn't have more damage. So the goal was reached, to have the plastic hinge where we wanted, and to have a capacity protected element for this specific configuration of external socket connection. We are also developing analytical models to change some parameters, so practitioners, engineers will be able to design with different parameters, not just following a specific one. But that's still a work in progress. So here, just a comparison between a cast-in-place concrete column, it's the red one, with a column with the external socket connection. You can see it's not the same. It was just a very similar concrete column, but it's a real column. We tested that column at NC State some years ago. You can see that it's very similar, the behavior. And with this, you can say that the external socket connection can be considered emulative. That means can simulate the behavior of the cast in place. And with that, I will bring some challenges and limitations of ABC connections in Central and Eastern US. The first one is the connectivity issues, because we need to be sure that we can withstand seismic actions. And it's not like only just for high seismic regions. No, we need to be able to withstand those even in low seismic regions. So we need to detail those or to be sure that they can withstand all seismic actions and all the different type of connections, not only the ones that I was showing here. So we need to prove a stiffness to those connections so we can maintain the bridge superstructure continuity also, and especially in regions as South Carolina with wind. We cannot have just flexible structures, as I mentioned. It needs to withstand different actions. But it's possible, but it needs more study, all the different types of connections. Maintaining the quality, we will need high quality materials, especially if you can do those in your shop and you will be fabricating those. Expert fabrication, so you will have You will need a specific shop so you can prefabricate all your elements. The type tolerances and quality control. You will need to be sure that your quality control is high. And adapting to environmental conditions, for example, temperature changes, that will be one. And as conclusions, well, the benefits outweighs the challenges. So there are some challenges. We need more research also in different type of connections, and we can also develop more. But those challenges, well, or the benefits that we will have, as I mentioned before, all those, and we can have more, those will always weigh more than the challenges. So it's worth to try using IBC connections for different projects that we have in the future, that we will have. But it's also important, the training and education. In education, it's part of that is research. We need to do more research on those to be sure that those can be implemented and that they will work as well as cast in place. But also skill training, so with in general, contractors and constructor people, and also the engineers, how to design those, how to detail this type of connection across the central and eastern U.S. And that will be all for me. Thank you.